Hello friends. So if you're seeing this video, I'm not in class today. However, I am here still to walk you through your first lesson of Unit 3, which we are doing quadratic functions, which this should be familiar to you. You did quadratic functions all throughout grade 10. Specifically, you learned what quadratic functions were, you learned how to factor them, you learned how to graph them, you learned how to solve them. You have quite the experience working with quadratic functions. So you'll find that today's lesson is really just kind of like a review. We're jumping back in. Maybe it's been a minute, so we're going to review some key terms and some key ideas, specifically when it comes to both graphing a parabola and then also like analyzing the shape of a parabola in the terms of like a real life scenario. So, okay, first things first, I've got this diagram of a parabola here, and I've got some key features that are really important for us to keep in mind for graphing and for word problems. So, okay, first things first, my x-intercepts, which I'll write here, my first bar, is where the parabola is crossing the x-axis, or we can think of it as where y is equal to 0. There's a couple names for the x-intercepts. We can call them zeros or roots or just plain x-intercepts, but they are here. I'll just call them x-ints. This parabola has two, but we're going to learn sometimes a parabola could have one x-intercept, sometimes it can have none, so those are our options. Next up, we've got our y-intercept. And this is really similar to the x-intercept in the sense of this is where the parabola is crossing the y-axis, or where x is going to be equal to 0. So right here is going to be our y-intercept. Then we've got our vertex. The vertex this is where our parabola is changing direction. So it is the maximum or minimum point of the parabola, depending on what the direction of opening is, but it is that change of direction or like the U shape of the actual parabola, which is going to be at the bottom here. And then last but not least, we've got the axis of symmetry. And it's kind of in the word when we're talking about symmetry, we're looking for the line that can directly cut this parabola in half. And we usually use it with this dotted line, as you can see in the image. And it's going directly through the x value of the vertex. So that is one way we can kind of define it or relate it to the vertex. When we get into graphing, parent function of just x squared, since that is like our OG parabola, we like to use step pattern. Step pattern, not sure if you learned it in grade 10. My grade 10s, I know you learned it. I definitely taught this to you. It is just like a faster way of graphing a parabola. So I'm going to just draw a quick little x and y axes here. And you will see how this is going to make your life so much easier. Here, I'm going to go all the way down here to make room since this is just our parent function. So rather than like plugging in values into your calculator, which like you can always do, worst case scenario, you can just plug in values into your function and do, okay, -2 squared, -1 squared, 0 squared, 1 squared, and so on and so forth. It's just going to take a little bit of time, especially as your equation starts to get a little bit more complicated and you've got more parameters involved. So step pattern is your easiest bet. For a regular parabola with no coefficient in front, just like x squared, the pattern rule is that we're going to go over 1, up 1, over 1, up 3, over 1, up 5, and then this rule would continue to go up by odd numbers. So the next ones would be like 7, 9, 11, 13, so on and so forth. So we are always going to start at 0, 0 for our origin, for the original. And I'm going to just follow this rule and I can mirror it on both sides since like this is a symmetrical shape. So over 1, up 1 should bring me here. And I'm just doing the same thing on the other side. Next I'm going over 1, up 3. Same thing on the other side. And then lastly, over 1, up 5. And same thing on the other side. And that is more than enough for us to connect and draw our parabola. And it's okay if she's wonky. just be as accurate as possible. So if I had to list some key features here for this parabola, like my vertex, I can see, okay, my starting point, the minimum point of this parabola, where it changes direction is located at 0, 0, or the origin. The domain of this function, or I can remind you all the x values that this function is allowed to take on or be with a parabola, those arrow means that it's going to continue on forever and ever and ever. So no restrictions. So I can just say XER. However, for the range, which is all the y values that this parabola can be, we see that we're kind of restricted to only positive values here. It's not going to dip into the negatives all of a sudden and change direction. It's only going to get more positively large. So I gotta say that YER such that y is going to be greater than or equal to 0. And that is your standard parabola. You can apply step pattern rule to any parabola, and you're going to see that if you have a coefficient in front of your leading term or your a value, whatever your a value may be, you're just going to times these values by a. So in this case, because our a value is 1, I didn't have to times it by anything. It's just the standard rule. But if my a value was 2, so like 2x squared, I would times everything I'm going up by 2. If it was -3, the negative just means that I would be facing downward. So I'd be going down in my step pattern rule, but I would still be timesing all of these values by 3. So you're going to see that in an example coming later in this lesson. And as you remember from grade 10, there are different ways that we can express a quadratic function. Specifically, there's 3, and they are standard form, factored form, vertex form. Each form has their own shtick, their own thing that makes them special. Each form also shows you different pieces of information about a parabola. So depending on what you're trying to find or what you're looking for, how you're trying to graph, it might make you want to find it in one form versus the other. So first and foremost, standard form, which I think is the form that you were introduced to the parabola by, it is just f of x is equal to, and then this is your standard ax squared plus bx plus c. So like a normal trinomial of degree 2. The only key features you can really tell from standard form is the direction of opening. So if a is positive, it's opening upwards or smiling, and if a is negative, it's opening downwards or frowning. And you can also determine the y-intercept because it will always just be your c value or whatever your constant is at the end. So those are 2 key characteristics that you can determine from standard form, but otherwise not the most useful form. More useful forms are, for example, factored form, which is in this format where you've still got f of x, I'm going to call it that. You've got an a value in front, and then you have your 2 brackets, x minus r and x minus s. So like, for example, in the last unit, for rational expressions, this was the form you were trying to get to. You were trying to get to these brackets. These are your x-intercepts. That is what r and s are. So they are telling you where your parabola is going to cross the x-axis. And similar to above, the a value can tell you the direction of opening. Last but not least, and I think everyone's favorite form for parabolas, is vertex form, which is in this form where we've got a and then we have x minus h squared plus k. This tells us a little bit more information, or it's a little bit more easier to visualize a parabola in this form because it tells you the vertex. So it's telling you your starting point, it's telling you direction of opening, and that already is super helpful when it comes to graphing. So your vertex is going to be HK. And when I say HK, we're thinking like opposite sign of this. So for example, something that was like, I'm just going to say in pink, x plus 3 squared minus 4. Our vertex then would be -3, -4. So you'll always flip the sign of what's in the bracket. So you're only just looking at the h, not necessarily the minus sign in front of it. K gets to stay the same. It's untouched. Right? We still know direction of opening because of A, And because we know the vertex, I know what the axis of symmetry is because it's just going to be my h value or the x value of my vertex. So that's the breakdown of the three forms, and you can always switch between the forms. So how we can go between the forms, we have to use some different methods. So for example, if I want to go from standard form to a factored form, I need to do factoring. So I need to either use product and sum or a ratio method. Right? Those are my two options. Versus if I want to go from factored to standard, I would need to expand, FOIL, and collect like terms in order to get back into a trinomial. And so they're kind of the opposite of each other. If I wanted to move on to the next one and go from standard to vertex, this is a little more steps. It's also people's like least favorite thing from grade 10, but it is completing the square. Complete the square, which we're going to spend a whole lesson doing, not this lesson, but we will be reviewing how to complete the square in case you forgot. But that is how you would go from standard to vertex and vice versa. If I want to go from vertex to standard form, I would need to, again, expand my bracket, x minus h squared, to x minus h times x minus h, FOIL, and collect like terms. And then last but not least, going between factored and vertex. Factored, unfortunately, there's no nice way to go about it. We would have to expand the brackets to get into standard form. And then FOIL and collect like terms. So no nice way to go about it. If I want to do the reverse, vertex to factored, again, I kind of have to do a little bit of extra work. We would have to expand our expression to a trinomial and then just do product and sum. And product and sum. I'll just say that. So definitely kind of like the harder, longer ways to go about switching between the form, specifically for factored and vertex. The other two are a little shorter or a little more intuitive, but still possible. So moving into actually now looking at a graph and talking about the characteristics as well as graphing, that's what we're going to get into here on this page. So we're given this example, we're given a graph of a parabola, and I need to state all of these key features below. First and foremost, direction of opening. It is frowning. Here are my eyes. You can see it's like a frowny face. So we know that it is downward, which tells us that our A value is negative. Just in case we have to come up with an equation, I'll erase these frowny eyes. Next up, we've got our vertex, or where we're changing direction. It looks like we've got a maximum point here that's happening right at 0, 2. So that would be our vertex. And we can just state it as a coordinate point. If I'm looking for x-intercepts, I'm looking for where is it crossing this line, x, which it looks like I'm crossing at 2 points. I'm crossing at -2 and 2. You can list them as coordinate points, so -2, 0, and 2, 0. I'm also okay with you just stating like x equals -2 and x equals 2 if you want to state that as well. Both are equivalent. I'm okay with that. Y-intercept, we're looking at where is it crossing this vertical green line, which seems to be where our vertex is, at 2. So again, we can state it as a coordinate point, which would be 0, 2. Or you can just say when y equals 2. That's fine. Lastly, our axis of symmetry. We said that's the dotted line that's going to perfectly cut this parabola in half, which we can see this is going through our x value of the vertex, and our x value of the vertex is just 0. This is kind of going through almost like the y-axis perfectly. So we can just say this is when x is equal to to 0. And you're done. Right? If I give you an equation and now I want you to graph and state these key characteristics, the hardest part is just going to be graphing. Once you've got the visual, determining these characteristics is not as bad. So first and foremost, I have to think of, where is my vertex from this equation here? Which, remember, on the back page, I just told you, we're going to flip the sign of what's in the bracket. So even though I see a -1, I know that it will be +1. And then k stays the same, so it's really 2. So even I'm going to write this here perfectly in the vertex spot. So it's going to be at 1, 2. That's going to be my starting point. So I'm going to go ahead and just plop that right there. 1 and 2 should be here. If I'm looking at direction of opening, I'm looking at the term of my leading coefficient, which it looks like it's negative. And we said negative means frowning or opening downward. So this also gives me like a little bit of help in terms of like visualizing what this is going to look like. I don't know my x-intercepts or my y-intercepts yet. I don't know the rest of this stuff because I need to like graph this first in order to determine those kinds of things. I can't just tell by looking at the equation. So I need to graph. And I'm going to use my handy dandy step pattern at the bottom of the page here. So we know that we said for a regular parabola with no coefficient in front, it would just be over 1, up 1, over 1, up 3, and over 1, up 5. However, we do have a coefficient in front of our function, or like we have an a value, which this is our a value here in front. So I got to multiply what I'm going up by this value here. So I'm going to times this by -1/2. So this really now means that I'm going over 1. So what I go over by does not change. That stays the same. But now I'm going to be going down. 1 times 1/2 is just 1/2. Or 0.5. Right? So the negative sign, remember, tells me the direction I'm traveling in. And then I'm just timesing whatever the value is by my coefficient in front. Same thing. I'm going to go over 1 still, but now I'm going down. And I'm going down 3 times 1/2. So 3 over 2 or 1.5. And lastly, same thing, over 1, but now I'm going down 5 times 1/2 or 5 over 2, which is 2.5. So, okay, that's what I'm going to do to draw my graph. So I'm going to start at this point here, and I'm going over 1, down 1/2, which looks like it brings me here. Then I'm going over 1, down 1.5. So I'm going to finish the half from this cube, and then it looks like I'm going to hit the x-axis. Same thing here. And then lastly, over 1, down 2.5, which looks like it would bring me to -2.5 for a y value. And that looks like enough for me to connect. You could continue the step pattern if you want to be super accurate in your graphing and you want to get more points here, but this looks like it's more than enough. So I'm just going to connect the points that we've got here and see. Okay, and just draw some arrows to indicate that it's continuing on. Make these dots like a little bigger. And now I've got more than enough of a visual to see what is going on with this parabola to name some of its key characteristics. So now I can see, for example, its x-intercepts. I couldn't see that before. I can see that they're clearly happening at -1, 0, and at, it looks like 3, 0. So that's where I'm crossing x. My y-intercept, I can see that was like one of the first points that I had done from my step pattern rule. And it looks like it's happening at 1.5. So I'm going to state this as a coordinate point. So it's happening at 0, 1.5. Or when y is equal to 1.5. And my axis of symmetry, that is what's going through my vertex, or my x value of my vertex specifically. I can see from up above that my x value of the vertex is 1. So I know that if I send a dotted line through this parabola. Again, it's going through x equals 1. So that is going to be the equation of my axis of symmetry. And that is how you're going to graph a parabola. So I promise you step pattern is your friend. I could have tested points individually, sending it through the given function equation. It's just going to take really long. So that's why step pattern, I promise, is super helpful for graphing parabolas. The last thing that we are going to talk about together is now using parabolas to model real life scenarios, or analyzing parabolas to determine like what's happening in a real life scenario. So the scenario that I gave you was a construction worker repairing a window, and he tosses his tool to his partner across the street. The height of the tool above the ground is modeled by a quadratic function, where this is modeling its height, and then t is the time in seconds after its toss. And it wants to know how high above the window, or how high above the ground is the window, I should say. So if I even had to like sketch this as a real life scenario, right? Here's your windowsill, I'll imagine. Right, and here's your person in the house working, and you've got some tool. And if they throw this hammer, which, oh God, I'm not an artist. I think that's like what a hammer looks like. That's actually not that bad. So if they throw it, now I'm getting all detail oriented. They're wearing a hard hat. Okay, I think I ended my artistic ability here. Here's his friend. You don't have to get this detailed into a test, but just in case, just to give you the visual, if he's tossing this tool and it's going to land eventually to his friend down here, how high it is your y-intercept. That's what you can think about it. This is your vertical, this is your horizontal. So the ground you can think of as your x-axis, and now this vertical, so like the building, the window, that's going to be your y-axis. If we want to know our y-intercept, the height of the tool before it's even been thrown out the window is when time is equal to 0. It's equal to 0 because it's like the tool hasn't been thrown yet. So it's still in its initial position. So if I want to find that out, I'm just going to plug in 0 into this whole function. So -5 times 0 squared plus 20 times 5 and plus 25. And you'll notice your first two terms are going to go to 0. Right? This is going to cancel out. This is going to cancel out. So you're only going to be left with your last term. So 25. So therefore, the initial height of the tool is 25 meters. So anytime a word problem is going to ask you about initial height, or how high something was initially before it was thrown or kicked, or whatever the scenario may be, it's talking about your y-intercept. Just like if it says his partner misses the tool, when will it hit the ground? If you're talking about hitting the ground, I'm just going to copy my beautiful diagram that I actually did here. I'm going to paste it. If it's going to hit the ground, now we're looking at when x is our intercept, or like when is it going to hit the ground? We're looking for the x-intercept. We're looking for when y is equal to 0. So now we're looking for this point here, which I'm going to erase just to keep it consistent. So we're looking for this point. And if we're looking for x-intercept, this is not when time is equal to 0. We have no clue what time it's going to hit the ground, but we do know its height will be 0. So I'm going to say that 0 is equal to h of t. 0 is equal to our height function. So I'm just going to say 0 is equal to -5t squared plus 20t plus 25. Now it's like, oh, how do we go about solving that? How do we go about figuring out what t is? Well, this is a trinomial. It's in standard form. I need to figure out what t is. I could use a couple different methods. I could use the quadratic formula, or more intuitively and just right off the tail end of what you just did in the last unit, you can factor that. So like, for example, I personally see that you can take out a -5 out of all these terms. They're all divisible by -5, which should leave you with just t squared minus 4t minus 5. And then you can easily do product and sum with that bracket. So product -5 and sum -4. That looks like it could be -5 and 1. Because I have no coefficient in front of this t squared within the brackets, I can just pop those values into brackets. So I should be left with -5 and then t minus 5 and t plus 1. Now, when you go to test these brackets, this is not your final answer because you have to tell me what t is equal to actually, right? And if we want to know what t is equal to specifically, it's like we're testing each of these brackets. Think about like what you did when you were solving for an asymptote. So, okay, we said t minus 5 is equal to 0 or t is equal to 5. So that's one option for an x-intercept. If I go to do this one, t plus 1 equals 0, or if I move the 1 over, it's going to give me t is equal to -1. One of these options does not make sense. Hitting the ground after 5 seconds of being thrown and being in the air, that does make sense. Whereas hitting the ground at -1 second, that doesn't make any sense. So I'm going to tell you right now, this is not applicable. Time cannot be negative, right? Time being negative means like you're time traveling. You're going back in time to before the tool was even thrown out the window. So that does not make any sense. So in a real world scenario, just like we did in Unit 1, you're going to have restrictions to your domain and range. You're going to have restrictions to what x and y are allowed to be because, for example, height and time don't really make sense being negative here, right? Working on to C, another thing, we're saying if the path of the tool's height were graphed, where would the x or the axis of symmetry be? We already talked about that. So again, where this tool is being thrown, I'm going to paste again my lovely diagram. I'm going to make it a little smaller just to fit in here. If we're talking about the axis of symmetry, we said that that is at the vertex. So I'm going to just draw a little dotted line here. And I'm going to write that this is our x-vertex. The axis of symmetry is going to be right in between. So if we've got our two x-intercepts, I can determine exactly what that is going to be if I add them together and divide by 2. So I don't know if you remember this AOS equation, but you can find it if you add your two x-intercepts and divide by 2, which in this case is going to be -1 and 5, which should give me 4/2, which is just 2. So this whole statement just means the maximum height of this tool will occur after 2 seconds. So your axis of symmetry or your x value of the vertex, that's telling you when it's going to hit max height. Not what the max height is, but when is it going to happen? So in this case, I was able to determine it using my 2 zeros, and it is going to be after 2 seconds of being in the air. It will hit its maximum height. Last but not least, domain and range, something that you are super familiar with now. Like I just mentioned earlier, we've got some restrictions. It just can't be XER or YER. It just can't be anything you want. We are constricted to real life scenarios. We're constricted to real life restrictions, basically. So we have to be considering that time can't be negative and height can't be negative. So if I'm just looking at the scenario of them throwing it out the window, my domain is going to be representing time. So the time that this is allowed to be happening at, I'm going to use t, since t is my variable for time. So I'm saying TER, but now I have to think about it like, okay, My domain is constricted from when the person is first holding the tool to when it hits the ground. That is what I'm looking at. So between, in this case, 0 to 5 seconds. Since we determined in part B, 5 seconds is when it's going to hit the ground. So that is our domain for this function. And I'm going to do the same thing with range, where range is going to be talking about our height. Again, in this case, I'm going to use h as our variable. And I have to think, I'm restricted to my highest value that this tool can be would be like the maximum height of this function. And then the lowest that this tool could be, the lowest height possible, is when it's hitting the ground. And that is when the height is 0. So I'm constricted to 0. And then I'm just going to write here f of 2, or even h of 2, I should say, to be consistent, h of 2, since we didn't actually solve for like what the maximum height is going to be. So you can just say like that y value. If I wanted to actually solve it, you could just plug in 2 into your original equation all the way up here. So you could say like, what is h of 2 if you want to know the actual height at 2 seconds. And I will actually spoil it for you. It is 45. So the maximum height of this tool is going to be 45 meters. And that's it. So that's your intro back into quadratics. I attached some practice problems here, which it's just really relative to like the things that we talked about in the lesson, going over key characteristics and graphing parabolas. If you got any questions about this, you can let me know on Tuesday when I see you again. But otherwise, have a great rest of your day, and I'll catch you next time.